Picking up where we left off, let's talk properties of vector algebra in Rn. So two things we can do to vectors. We can add them together and we can multiply them by scalars. And this is given some of the properties of those two algebraic operations. Theorem 1.1 says that if we take any vectors u, v, and w in Rn and any scalars R and S, any real numbers R and S, then we get the following bunch of properties. And they've divided these into properties that they've numbered with A's, A1 through A4, and four other properties, S1 through S4. And the A properties deal with the addition of vectors, and the S properties deal with scalar multiplication, the two things we can do with vectors. And the properties are that we've got associativity of vector addition, that is the sum of vectors u and v plus w is the same as the sum of u plus the sum v and w. We can do the addition with the u's and the v's first, or we can do the addition with the v's and w first. Usual associativity property, but for vector addition versus number addition, say. We've got commutativity of vector addition, vector u plus vector w equals vector w plus vector v. We've got an additive identity. The zero vector added to any vector gives back that vector, just as zero is the additive identity number. Zero plus any number equals that number itself. We've got additive inverses. If we take vector v and add to it negative vector v, we'll get out the zero vector. In terms of properties of scalar multiplication, we've got distribution, legitimate distribution now. Scalar distribution of scalar multiplication over vector addition. If we take scalar r times the vector sum v plus w, we get r times vector v plus r times vector w. So distribution, we commented in the past, you need two operations to have a distribution property. Here we've got the operation of scalar multiplication right there, and the property of vector addition right there. Similarly, we can have a distribution of scalar addition over scalar multiplication. Scalars r plus s times vector v equals scalar r times vector v plus scalar s times vector v. Here we've got right there the scalar multiplication operation, and here's the second operation, scalar addition right there. For distribution, you have to have two operations. In this case, two operations, both in S1 and S2. We get an associativity in the following sense. If we take scalar r times scalar s times vector v, that's the same as scalar product rs, numbers r times s, times vector v. So the associativity is between the scalar and the vector on the left and between the two scalars on the right. And something these guys call preservation of scale. I'm not sure that's a universal term, but Fraley and Beauregard refer to the fact that scalar 1 times vector v equals vector v. They can title that preservation of scale. Let's prove a little bit of this. Let's see, proofs of the A2, the commutativity, and S2, the distribution in this sense, are given in examples in the book. Some of the exercises gives proofs of these. Let's go through a couple of those. Let's look at proof of A1, the associativity, and S1, the distribution. So let's look at proofs of this property A1 and this property S1 by going to supplements. Okay, in the supplements, we want to prove that for any vectors u, v, and w and r and s, any scalars, that was a setup in the theorem, though this only deals with the vectors, that if we add u and v first and then add w, that's the same as adding v and w first and then adding u in this sense. Okay, these vectors are from Rn. You know how you add vectors in Rn. You add them component-wise because that's a definition. So take your vectors, u, v, and w from Rn. I tell you what, let's write them in terms of components because that's how we're going to add them together. So let vector u have components, u1, u2 through u sub n, and similarly for vector v and similarly for vector w. So we'll write these in terms of components. So we can take the left-hand side, u plus v plus w. We'll go through and turn that into the right-hand side and do so by using the definition of vector addition. So we'll take vector u plus vector v, that'd be u1 through u sub n, plus v1 through v sub n, bracket those together, do this addition first, and then we'll add on vector w as given on the left-hand side of the property. How do you add u and v together? Component-wise, of course. So add u1 and v1 to get the first component, u2 plus v2 to get the second component, and so forth. All right, definition of vector addition. Now we've got, quite technically, you only add two vectors together at a time. Of course, we're in the process of learning some shortcuts on that. But now we want to take the vector with these components and add it to the vector with the components of the w's. We've added u1 and v1 first, so we'll bracket those together, and then we're adding w sub 1. We've added u2 and v2 first, so we'll bracket those together, and now we're adding w sub 2, and similarly throughout. Why? Vector addition. All right. Now we're trying effectively to move these parentheses from the u and the v vectors to the v and the w vectors. Well, here we are, component-wise, in a setting where we have, for example, in the first component, this number plus this number, u1 plus v1, added together first, plus w sub 1. Well, we've got associativity of real numbers, so we could move the parentheses in this first component from u1 and v1 to v1 and w1 because you've got associativity for addition of real numbers. In fact, you can do that for each of the components. This is where the associativity is happening. For those of you with more theoretical math classes ahead of you, this is a common thing. You're asked to show associativity of vector addition. Well, we've taken that question, used the definition of vector addition, and translated it into a new setting, a setting where we know that we've got associativity. That setting is the real numbers. The components are real numbers, so I know how real numbers behave. We've changed it into a question involving components. We've used associativity on those components because those components are real numbers. So the big picture here is we've taken a question where we're trying to establish something new, and we've translated it into a setting where we already know that property holds. For example, associativity holds in the real numbers. We've used associativity in that familiar setting, the real numbers. Now we just got to unwind it. So we'll take this, use our definitions of vector addition, and basically work backwards to go back into the vector notation. All right, so we left off with this on the previous slide. So we can write this then as we've got one real number plus a second real number in the first component, a real number plus a second real number in the second component, and so forth throughout. Those first real numbers are the u's, and the second real numbers are v1 plus w1, v2 plus w2. So in terms of a vector sum, by the definition of vector addition, we can write this previous line in terms of this vector sum. And just as we did on the previous slide, except we're going the other way now, now we can take this vector and recognize it as a particular vector sum. This is vector v1, v2 through v sub n plus vector w1, w2 through w sub n. Though we're doing this addition at this stage, so we're bracketing these two together. And if we'll translate this back into the symbols, u vector, v vector, w vector, that's exactly the other side of the equation. So straightforward, if you're not comfortable with proofs, they can't get much more elementary than this. We took the left-hand side of the equation, we turn it into the right-hand side of the equation. You may not be that familiar with proofs, but you've done trig identities before, I'm sure. You need those in calculus too when you do trig substitution. You've dealt with trig identities along your career. All right, this is the same kind of thing. In a trig identity, you take one side of the equation and turn it into the other using information you know, which is probably more elementary trig identities in that setting. Here, we don't know much, but we brought into this class with us knowledge of the properties of the real numbers. So we started with the left-hand side, turned it into a question involving real numbers, used associativity there, unwound it into the right-hand side. So we've shown the left-hand side equals the right-hand side. There's your proof. Let's do it again for property S1, distribution. R times vector V plus vector W equals R times V plus R times W. How are you going to do this? Well, write V and W in terms of components, and I bet there'll be distribution from the real setting somewhere in here. And that distribution in the real setting will arise in the setting of components. The components of all our vectors are real numbers. Okay? So write V and W in terms of their components in the standard way, this stage. Then we'll take R times V plus W. Okay, in terms of components, that's R times this vector with the V's plus this vector with the W's. How do you add vectors together? Component-wise, because that's what definition 1.1 part 1 tells you to do. So add those vectors together. How do you multiply by scalars? You take the scalar and you put it on each of the components. As mentioned before, that's not distribution. That's the definition of scalar multiplication. That's not a distribution property. That's a definition. Definition 1.1 part 3. Ooh, but look what we got for components now. We've got this real number times the sum of those two real numbers. Well, I can distribute this real number onto each of those real numbers because that's a property of real numbers. The components are real numbers. With the real numbers, we have that multiplication distributes over addition of real numbers. So this R being distributed on that V1 and V2, that's distribution. This R being distributed on that V2 and that W2, that's distribution, and so forth throughout each of the components. All right, so how are we doing here? We dealt with distribution from the real numbers, so this must be the real load-bearing bit of the work. We need to, turn it into this type of equation. This is a sum of two vectors. Do you see how you could write this as a sum of two vectors? Certainly. We've got a first number plus a second number in each of the components. Here's what we had on the previous slide. Well, then we can collect together the first numbers and the second numbers into constituent vectors. That's the definition of vector addition again. All right. Now we've got it as a vector sum. We got only V's in this one and only W's in this one. Actually, there's R's all over the place. We can factor this R out. No. Factoring is kind of distribution backwards. No, you don't factor it out. You use the definition of scalar multiplication. I mean, you bring it out front for sure, but technically that's the definition of scalar multiplication. That's not a distribution there. We saw the distribution at the bottom of the previous slide. So bring the R's outside, definition of scalar multiplication. In both of those, rewrite this n tuple as vector V and this n tuple as vector W, and we've turned the left-hand side into the right-hand side and established that proof. Back to the notes. Okay, so what do you know now about vector algebra? You know, in addition to the definition, you know these 8 properties here. And that's all you know, so that's all we can use at this stage. We're going to get a lot of mileage out of just these 8 properties, it turns out. Some geometric interpretations Definition 1.2 says, two non-zero vectors, v and w, in Rn, all our vectors will be from Rn in Chapter 1 and Chapter 2. Not all our vectors throughout this course will be from Rn. We'll see some other vectors, but Chapters 1 and 2, vectors from Rn. Two non-zero vectors, v and w, are said to be parallel, denoted with two little vertical lines as given here. Probably a symbol you had in high school geometry when you talked about parallel lines. So this is something new. This is parallel vectors. These vectors are said to be parallel if one is a scalar multiple of the other. That is, if v equals r times w for some scalar r greater than 0. If r equals 0, we're going to end up with a contradiction to the fact that we're only talking about non-zero vectors here. If r is greater than 0 and we get v equals r times w, then they're said to be parallel and with the same direction. So they're defining same direction. If that scalar multiple, v equals rw, that scalar r is negative, then they're said to be parallel with opposite directions. So this isn't a universal thing, but Fraley and Beauregard are distinguishing between this kind of parallel and this kind of parallel. Parallel with opposite directions, parallel with the same direction in terms of vectors. Some folks would call this anti-parallel and this parallel. So the verbiage isn't universal. We'll follow these guys' terminology, but you may run across an idea of anti-parallel vectors. You wouldn't talk about anti-parallel lines, and you wouldn't talk about directions of lines. That's not a property of lines. Lines are just sets of points. They have, in R2, they have slopes. In Rn, they might have direction vectors. In fact, we'll see something like that shortly. But you don't talk about the direction of a line. You talk about the direction of vectors. We're interpreting vectors as informally, a wink, as magnitude and direction. But we haven't defined magnitude nor direction yet. But you brought that knowledge in with you probably from physics experience and possibly from some math experience in your past as well. But we'll think of vectors as having directions, or directions are actually represented by vectors in some sense. Okay, so we could test for parallelness by seeing if one vector is a scalar multiple of the other. Let's do that here. Okay, let's look at number 22. It says, find a scalar c, if there is such a scalar, such that the vector c squared negative 4 is parallel to the vector 1, negative 2. All right, you know what parallel means. It means one's a scalar multiple of the other. So we need to find a non-zero scalar r such that the first vector c squared, comma, negative 4 equals r times the second vector, 1, negative 2. All right, we're requiring these two vectors to be equal. That means that their components are equal. If we'll use the definition of scalar multiplication, we'll take this r inside on those components. Then we'll get c squared, comma, negative 4 equals r, comma, negative 2. We need the first components to be the same, and we need the second components to be the same. Remember, the question is, find c. Now we got c and r in the story. And we'll probably find r first, and then find c based on that. So we need the first components to be the same. We need c squared to equal r, and we need the second components to be the same. We need negative 4 to equal negative 2r. So let's see, from the second components, divide both sides by negative 2, you see that we must have r equals 2. If r equals 2, plug that back in over here, then we get c squared equals 2. C squared equals 2 means c is either square root of 2 or negative square root of 2. So we've ultimately dealt with this vector equation. Here it is. This vector equation right here yields two equations, one for each component. This one for the first component and this one for the second component. So we've actually solved these two equations together. We'll talk about systems of equations at great length here fairly soon, the next 2 or 3 sections. But we've satisfied the second equation to find R, plug that in. That gives us a condition on C. If C is square root of 2 or negative square root of 2, then we will have these vectors be parallel. Yeah, that's because then C squared equals 2 in either case. We've got the vector 2, negative 4. You sure that's parallel to 1 times negative 2? Yeah, we took R to be 2, and if I multiply this vector by 2, we'll get 2, negative 4. And if we take C to be the square root of 2, or negative square root of 2, we'll get 2, negative 4 here as well. So those are, in fact, parallel. I guess I could add a little bit of info to this. R is positive, so they're parallel with the same direction, though they didn't ask that in the question. Back to the notes. Okay, this we actually saw this terminology in one of the first questions we looked at. The definition now finally of linear combination. This must be a big deal because it's a linear algebra class. This is the linear in linear algebra. Surprisingly, looking at it, I'm not sure I see too much that reminds me of lines from high school algebra. So the linear in linear algebra is way more this than it is a concept of lines, as you might think. Given vectors, v1 through v sub k and Rn, and given k scalars, one for each vector, the vector we get by taking the first scalar times the first vector, plus second scalar times second vector, plus blah, 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 last scalar times last vector. For fans of summation notation, we could write it, say, sum from L equals 1 to k, R sub k, V sub L. So you're adding together a total of k vectors, each one with a coefficient. So I've thrown that word around probably in the past. We're finally formally defining the coefficients. I can highlight it here, the coefficients, there we go, of a vector. And of course, they're scalars. Doesn't make any sense to multiply one vector by another. That we haven't done. That's undefined algebra. Our algebra is adding vectors together and multiplying them by scalars. Doing a bunch of that creates what's called a linear combination. It's just a big collection of the stuff we do to vectors. We multiply them by scalars and we add them together. Here you've taken a bunch of vectors and a bunch of scalars, multiplied the scalars times the vectors, and added what results together. So this is, in some sense, the most general thing that we can do with vectors is take linear combinations. This is linear algebra. This is what it's all about, it turns out. Okay. Wanting some interpretation of magnitude and direction, we're motivated to consider the following. The story might be a little dry in the short term, but we're going to see a great deal of this standard basis stuff and basis stuff in general. It'll be a section or two before, maybe even chapter 2 before we get into it in any detail. But we're interested in some special vectors. What makes them special is we can use them to express other vectors as linear combinations of these special vectors. The standard basis vectors in R2 definition are the vectors denoted I and j. The I vector has components 1, 0, and the j vector has components 0, 1. In 3 dimensions, the standard basis vectors are I, j, and k. I has components 1, 0, 0, j has components 0, 1, 0, k has components 0, 0, 1. I bet you could extend that to higher dimensions. In R4, we have 4 vectors. The IJK notation is pretty exclusive for just 2 and 3 dimensions, for R2 and R3. But if we move to 4 dimensions, I bet you we have 4 vectors, a 1 followed by 3 zeros, 0, 1, 0, 0, 0, 0, 1, 0, if it's got 4 components, and then 1 that's 3 zeros followed by a 1. More of that in a second. But these are defined as the standard basis vectors in R2 and R3, and as mentioned above, it's easy to write a vector in terms of the standard basis vectors. You want to write, say, vector B with components B1 and B2 as a linear combination of I and j, because this is a vector from R2, because it has 2 components, piece of cake. B1 times the first vector, the I vector, plus B2 times the J vector. We'll kind of intermingle this notation with I's, J's, or I's, J's, K's, and components. You're going to like the component notation better because it's the components you'll probably end up manipulating more often than not. So if they give us something in terms of I's and J's, maybe that's just fine, or maybe I'll turn that into components. It depends on the question. But more often than not, components are more useful things to consider than the IJ stuff. And there's a real equivalence between them in a sense. You want to write vector B with components B1, B2, B3, a vector from R3, as a linear combination of I, J, and K. Easy. You have to take B1 times the I vector plus B2 times the J vector plus B3 times the K vector. You do the arithmetic, you get B1 times 1 plus nothing for first components. You get first components B1. Similarly, B2 is a second component. It's contributed here because there's zeros in the middle of those other two vectors. And B3 comes out as a third component. There's zeros in the first two. So expressing this vector as a linear combination of these standard basis vectors, a piece of cake. We're going to have bases other than the standard bases, and we're going to write vectors in terms of those other basis vectors, and it's going to be more complicated. The zeros and the ones really paid off here. We might take those other vectors and complain about them at some point and change them into something more similar to the IJK idea with the zeros and the ones. More of that in the distant future, actually, when we do something called the Gram-Schmidt process in chapter 6. And moving beyond 3 dimensions, the rth standard basis vector in Rn is defined to be the vector, I should point out this notation, E, little caret over like a shift 6 on the keyboard. We use that same notation instead of the little vectors when we had the I's, J's, and K's. It's common to use the little hat when you have a vector of length 1. You know what I mean by length 1? We haven't defined length yet. I think we do in the next section. But these are all length 1 vectors, turns out, in the magnitude scale, the scheme of things. They're magnitude 1 vectors. But it's common to put this little caret symbol over the symbol that represents a vector of length 1. It's certainly common practice when you're dealing with I's, J's, K's, and these other standard basis vectors. So the rth standard basis vector, denoted, is given here, E sub r with a little hat over it, is the vector that has all components 0 except in the rth position indicated by this subscript. We've got a 1. So it's all zeros in a single 1. That 1 appearing in the rth position. We could call this vector here E sub 1 in R3. We could call this vector here E sub 2 in R3. This vector here is E sub 3 in R3. And we only get 3 such vectors in R3. In R4, we'd have E sub 1, E sub 2, E sub 3, E sub 4, just as described. Now, an observation about these standard basis vectors, shrink it a little bit so we can see both of those at the same time. If we wanted to write vector B in Rn with components B1 through B sub n as a linear combination of the E1s through E sub n's, well, that's easy, just like it was with the IJKs. We take the first component, the B sub 1, times the first basis vector. That first basis vector is a 1 followed by a bunch of zeros. All these other vectors are going to have 0 for the first component. So they ain't going to affect the first component, only the first one will. So we'll take B1 times E sub 1. Second component, well, that's only affected by the second basis vector. We'll take B2 times E sub 2, and so forth. So there's only one way to write, there's much there, only one way to express this vector as a linear combination of these standard basis vectors, and that's it, as you can tell by looking at individual components. This uniqueness and the fact that I boldfaced the word uniquely, is calling attention to something we'll see when we formally define a basis. So all we formally defined so far is what? Vector addition, vector subtraction, scalar multiplication, and linear combination and parallel vectors, I guess, is all we formally defined. But when we define basis, this unique linear combination thing will play a role. So we got a ways to go. To give more geometric interpretation, stuff we can see lines and planes. Higher than that in terms of dimensions, whatever dimension is, it's hard to visualize. But in our ongoing quest to try to draw pictures, we have the following definition. Take a single vector v from Rn, non-zero vector. The line along vector v is the collection of all vectors of the form r times v, where r is some scalar. If that scalar is 0, we get the zero vector. So the zero vector lies on all such lines. So all scalar multiples of a single vector is called the line along vector v. So there's something related to lines, not linear combinations though. And I'd love to draw pictures. One little problem is this is happening in Rn, and I can't visualize anything beyond R3. But I can take this as a definition. Fine, a line along vector v in Rn, just a collection of all scalar multiples of vector v. Suppose you took two non-zero, non-parallel vectors, v and w, from Rn. The collection of all possible linear combinations of those two, that'd be scalar times v plus scalar times w, r and s, or any scalars, is called the plane spanned by v and w. All right, so this word span is about to take on a more formal meaning, but the idea behind this is you take all scalar multiples of a vector, and we had a geometric interpretation of that. Here's the vector, multiply it by positive scalars, it keeps the same direction, maybe gets longer if the scalar's positive, shorter if the scalar's, it's longer if the scalar's greater than 1, shorter if the scalar's between 0 and 1, and points in the opposite direction if that scalar is negative. And the magnitude is determined by the size of the scalar. This should make some intuitive sense. Now I start trying to draw pictures. I got some problems seeing a line if I try to interpret this collection of vectors as a line, unless I put those vectors in standard position. Remember standard position? Put their tails at the origin. Then I can actually see a line. And a similar story with this. If I take all these bunches of vectors down here, they lie in a plane. They do lie in a plane if you put them all in standard position in a coordinate system. So we'll see some pictures on down the line, but these really do represent planes. But the only way you can have that geometric interpretation, I try to make a big deal out of this, that geometric interpretation is to put the vectors in standard position. Then you'll get yourself a bunch of vectors that lie in a plane. We'll elaborate on that as time goes by. But there's the definitions, a little bit more stuff just to get the ball rolling here in this first section. Column vectors are vectors represented vertically like this, as opposed to row vectors, which are vectors represented horizontally like this. So far, all the representations we've had of vectors, I think, have been row vectors. But we could well represent vectors as column vectors. We'll introduce this idea of a transpose of vectors. The transpose of a row vector is a column vector, and it's denoted by putting a little t superscript on there. It's not an exponent, it's an operation. It says take this column vector with entries x1 through x sub n, transpose it to create this row vector with entries x1 through xn, or take this row vector with entries x1 through xn, transpose it to create the corresponding column vector. So to transpose a vector is to switch it from a row vector to a column vector, or column vector to a row vector. When we hit matrices in a couple of sections, this transpose idea will play a bigger role. For now, just there it is, it's formally defined. We will largely not be too concerned between delineating between row vectors and column vectors. Kind of depends on the setting. when we deal with matrix multiplication, it's going to matter big time. But there's other settings where I'm not particularly hung up on whether we express vectors as rows or columns. We'll be a touch liberal in our use of the notation in those settings. Hey, suppose we took a linear combination of a couple of column vectors. Suppose we took r times this vector 1 at 1, 3, plus s times this vector negative 2, 5. And from that we got out, say, the vector with two components, negative 1, 19. To foreshadow some things to come and just to introduce, to expose you to some column vectors for something new. What if you did the arithmetic on the left-hand side? What would you get? R times 1 plus s times negative 2 for first component. You get r minus 2s for first component. On the right-hand side, you got negative 1 as a first component. For second component, you'd have 3r plus 5s, 3r plus 5s, right-hand side. Second component's 19. So having this linear combination with these maybe unknown coefficients r and s corresponds to having these two equations and two unknowns. So we can relate a linear combination, say of column vectors, I'm foreshadowing something here, as a system of, in this case, two equations and two unknowns. Two, because we had two vectors and they had two entries each. Two equations from the number of components, and two unknowns for maybe the unknown r's and s. You might try to find r and s that satisfies both of these equations. We're going to be doing a bunch of that once we get some equipment to handle it efficiently. We might do a little bit of it before we can efficiently handle it even. Okay, a little comment that's actually not in the book, but it's notation that the book uses. So let me run through this real quick. We need to discuss sets. We need to know what set notation means. Informally, informal set theory is quite involved, but informally a set, you know what a set is. It's just a collection of things, and the things are called elements of that set. We're most likely to deal with sets of vectors. So we might have V as the vectors, V1, V2, and V3. We'd denote this as V1 as an element of set V, V2 is an element of set V, and so is V3. But those little symbols there highlighted or red, V1 is an element of V or set V. We might describe sets by giving properties of the elements of that set. So what we're doing here is defining maybe a set of vectors V of the form x1, x2, x3, such that, this little vertical line means such that x sub 3 equals 0. So here we're taking all vectors from R3, so all vectors are 3 components, such that x sub 3, the third component, equals 0. So here's a set theoretic way to describe a collection of vectors. It's a subset of the collection of all vectors in R3, those whose third component are 0, by the way. One passing comment, this is maybe not totally important for what we'll do, but it certainly matters in what a set is. Things are either in a set or they ain't in a set. They're not in a set more than once. You don't repeat elements of a set. You either got, for us, this vector, it's either in this set V or it ain't and in that set V. It's not in there multiple times or something like that. There are things out there called multi-sets, but not our problem. You want some formal set theory, help yourself. I got some notes at this stage, sort of around summer 2020. These notes are fairly preliminary, but I've got a little bit of notes posted out on formal set theory. Unfortunately, we don't have a class on formal set theory. So we'll use some set notation to express various collections of vectors. Let's do that right now. Definition 1.4 is a definition of the span of a set of vectors. Last slide or so, we defined the plane spanned by two vectors, and that was really a special case of what we're about to do here. So here's a more formal definition of span and a more general idea. Take vectors v1 through v sub k from R sub n. The important thing is they all have the same number of components. They all have n components. The span of these vectors is the set of all linear combinations of those vectors. It's denoted SP. Some books actually write the word out, SPAN, but we'll denote it SP of this collection of vectors v1 through v sub k. So as a set, the span of those vectors is all linear combinations. Linear combinations look like this. So it's all R1 V1 plus R2 V2 up through R sub k V sub k, where the R's can be any real number. If you like summation notation, we can write it like this. There's your such stat symbol right there. Here it is to match up with the size of the set brackets. But we'll take linear combinations and allow the coefficients to be all real numbers. So every real number is used in producing the span of a set of vectors. If we took the span of one vector, we'd get the line spanned by that vector. If we took two vectors only, we get the plane spanned by those vectors as the span of that set of two vectors. So this overlaps with that geometric idea we were pushing a while ago. One final example, number 16, whoops, 16. Okay, question is, find all scalars C, if any, such that the vector I plus Cj plus C minus 1k is in the span of I plus 2j plus k plus 3i plus 6j plus 3k. So some practice with the ijk notation along with a practice of span. Some illustration of the idea of a span of two vectors in this case. Okay, the span of these two vectors, why, that would be the set of all linear combinations of those two vectors. So we can reword the question as, find a real number C, if any, such that the vector I plus Cj plus C minus 1k, this vector, is in the span of those two vectors, okay, is some linear combination of the two given vectors, the I plus 2j plus k and the other one. So can you find R1s and R2s such that the R1s and the R2s satisfy this equation, or for which values C are there R1s and R2s? So there's three things we don't know. We don't know R1, we don't know R2, and in particular, we don't know C, and that's the real question. But all we've done is translated their question involving the word span into our question involving linear combinations. Spans are linear combinations, so we hadn't done much yet. All right, if this equation holds, let's add these two vectors on the right-hand side of this particular equation. How many i's do we have? R1 plus 3R2 i's. How many j's? 2R1 plus 6R2. Distributing, really is distribution. And how many k's? So we'll do the addition on the right-hand side. We need the same number of i's on both sides. We need the same number of j's on both sides, and we need the same number of k's on both sides. Or you could write these in terms of components. First component over here is 1, second component is C, third component is C minus 1. Right-hand side, there's your first component, there's your second component, and there's the third component. And then we could set components equal to each other. So ijk, three components, same difference, as they say. So we need the number of i's on this side, 1, to equal the number of i's on this side, R1 plus 3R2. We need the number of j's to be the same, and we need the number of k's to be the same. Or if you like components, I like components, we need the first components to be the same, second and third components be the same. It generates three equations. So we get these three equations, and we need to find values of C that make this true for some R1 and R2. That's the question. Find scalar C such that this vector is in the span of these two vectors. That is, this vector is a linear, here it is, this vector is a linear combination of those two. for some R1 and R2. The ultimate question is find C. Along the way, we'll have to find R1s and R2s as well. All right, so here's a system of equations right here. I wish I had neat equipment to deal with it. We will. Right now, we're just going to kind of do this a wee bit sloppy. Let's take the first equation, numbered them. Let's multiply by 2. That'll give us 2 equals 2R1 plus 6R2. 2 equals 2R1 plus 6R2. Hey, and this is totally haphazard, that's why I'm explaining it this way. What the hell motivated you to multiply by 2? Well, now I see. When I multiply the first equation by 2, the right-hand side is the same as the right-hand side of equation 2. So if we've got 2 equals 2R1 plus 6R2, by doubling this, and we've got C equals 2R1 plus 6R2, then C must equal 2. The left-hand sides must be equal. So we found that C equals 2. So if anything works, it's going to have to be C equals 2. But I don't know necessarily, even with C equals 2, that we can find R1s and R2s that satisfy these equations. So we need to do that next. So if this works, it's going to work for C equals 2 by this argument from the first 2 equations. We didn't even use the third equation yet. Okay. Well, let's look at the third equation. If C equals 2, equation 3 would give us 2 minus 1 equals 1 equals R1 plus 3R2. Hey, that is equation 1. So it looks like it's going to work. So we need 1 to equal R1 plus 3R2. We need 2 to equal 2R1 plus 6R2, which if you divide by 2 actually produces the first equation. We really just need this first equation to be solved. What you've got here when C equals 2, you've got this equation. The second equation, C equals 2, this is twice the first equation, so it's no new information. And with C equals 2, the third equation is just a first equation. With C equals 2, you really don't have 3 different pieces of information. You've got 1 piece of information, and it's the first equation. So can you find R1 and R2 that satisfies the first equation? Because if you can, it'll satisfy the other 2 when C equals 2. Sure. How about R1 equals 1 and R2 equals 2? Plug in 1 there. I'm sorry. R1 equals 1 and R2 equals 0. Plug 1 there, 0 there. Sure enough, you get 1 out. And these others will be satisfied as well because they're redundant with that first equation. So it does work with C equals 2. And for example, R1 equals 1 and R2 equals 0. You don't like using 1 and 0? We'll use something else. As long as it satisfies the first equation, and there are an infinite number of choices, you're good to go. We could take R1 equals to 0 and R2 equals to 1/3. Now 1/3 here, 0 there, and that'd produce a 1. So there's another possible choice for R1 and R2. You don't take C equals 2, you'll have inconsistence between the first and second equations. So to answer the book's question, we take scalar C to be 2. And a habit I'll develop in these notes is if they ask for a specific number like they did in this one, I'll put a box around it. And here's my answer. If they ask for specific vectors, I'll put a box around the vectors. When it's time to take the test, I'll give you a test with room for you to work the questions on the test, and then I'll put a little box at the bottom and tell you to put your answer in the box at the bottom. So I'm mimicking the format of the test when I go through with this putting a box around the final answer. And sometimes the answer is some sort of logical argument, so it doesn't make sense to put a box around it then. But if it's a number or a vector or a handful of vectors, I'll give you boxes. And that takes care of section 1. So have a nice day. We'll move on to section 2 here shortly. Bye-bye.